Okay, we got I think there's a quiz due today, so if you haven't taken that one, make sure you take a look at that. It's some of the decimal stuff that we did up through about yesterday. Decimals up through equations with decimals. I don't think it has mean, median, or probability on it like we did yesterday, but it does go up through the equations. And I didn't get a chance to correct those ones last night. I ran out of time, but I'll get those back to you on Monday for those of you who turned them in. So, today we're going to finish off chapter 5, which was all about decimals and how they're related to fractions and working with decimals. So there's just a couple other concepts that I want to cover. Then that'll lead us really easily into chapter 6, where we're going to focus more next week on percentages and applications of percentages and proportions. So the first thing I want to talk about today is what we call ratios. So there's ratios and there's rates, and they're actually two different things. Okay. So for a ratio is I don't know where might have you encountered ratios. I'm not sure. Like if you're talking about a recipe. Okay, so let's say a recipe calls for 2 cups flour for every 1 cup, or let's say, I don't know, we'll just go 1 cup. 1 cup sugar or something like that. Okay. So this is a ratio. So the ratio here is what? It's 2 cups to every 1 cup, right? And a ratio can be written. You may have seen ratios written as with the colon in between them, like 2 to 1. But they can also be written as fractions. So this one right here, we could write this as 2 to 1, or we could write this as a fraction of 2 over 1, right? 2 to 1 or 2 over 1. Now you'll notice over here, I list it with no units, and ratios actually don't have units because ratios are comparing two things that have the same unit. And and the reason they don't have units is because if you think about this in terms of units, 2 cups to 1 cup, well, when I turn that into a fraction, 2 cups over 1 cups, well, if you have the same unit in the numerator as the unit in the denominator, the units actually cancel. Okay. And so what happens is you just end up with a fraction and you don't have any units left over. It's just 2 to 1. And so the thing about ratios have no units because they compare two values with the same unit, and because of that, they have no units. Okay, and this actually, if you think about it, for example, in this recipe, would you have to restrict yourself to only using 2 cups and 1 cup of sugar? Is that the only way you can make this recipe? Does it have to be that way? It doesn't have to, right? You could do what? If this one recipe, if this says this is 1 batch of cookies, what could you do? You could double it, or you could triple it, or you could half it. You could cut it in thirds. You could, right? You can change the values. What you have to do is you have to preserve the ratio, right? So I'll wait till you guys write that down, okay? Because I want to elaborate on this a little bit, okay? So if we're dealing with ratios, right, and the recipe says, that for 1 batch, it's 2 cups flour to 1 cup sugar, right? If that's the way the recipe calls it, okay, well then the ratio here would be 2 to 1, which would be 2 to 1. But you don't have to stick to cups, right? You could say you could call for, this would extrapolate out. If I wanted to half it, I could do 1 cup flour to what? What would I have to do? Half cup sugar, right? You can make it even like small. I mean, you don't even have to use cups or anything, right? Like, let's say that what if I have, what if I use like 3, what if I use 3 tablespoons of sugar? How much flour would I use? I could do it. What would I use? So 3 tablespoons of sugar would be, how much flour would I need? Two. Well, sugar, you need less sugar than flour. So let's say that I had this recipe and I was going to make it really small, and I have 3 tablespoons of sugar. I could still do the recipe. I'm just going to make a really small batch. But if I have 3 tablespoons of sugar, how much flour should I have based on the ratio? Should you have more sugar or more flour? You should have more flour than sugar based on the recipe. How much more? 2 to 1. Twice as much. So how much flour would you need? Yeah, right? You would do 6 tablespoons flour, right? So it doesn't matter the units. So here we were working with cups, then we were working with tablespoons, right? The units don't matter because it's just a ratio that preserves, the relationship between one thing to the other. So ratios don't have any units. If you had like a cup that wasn't actually a standard cup, you could still use it for the recipe. You just got to make sure if you put 1 of these in sugar that you put 2 of those things in flour. It doesn't matter if it's a standard cup. In fact, I was reading a recipe a little while ago, and it said something like, I can't remember. It was something like that, and it said something like it called for like 2 parts. I can't remember what it was, but it was something like that. It was like 2 parts sugar to 1 part, or it was. I think it was like for making gravy or something. It doesn't matter, but let's say it's like 2 parts sugar to 1 part. I don't know. What else do you bake with? I don't know, oil or something. Whatever, it doesn't matter. Okay, but they was saying 2 parts sugar to 1 part oil. That was what they were. That's what the recipe said. And one of the comments on the recipe was, "What's a part?" Right? That was what someone asked that question. Like, what's a part? Because it wasn't listed as like a cup or a tablespoon or thing. But does it actually matter? Do you need to use if all you care about is the ratio? Do I even need to list the units? You don't, right? Because all you need to know is that, well, however much oil you put in twice as much sugar. That's the rule, right? It doesn't matter how much you want to make, and then you can make the batch as small or as large as you want. Okay. So anyways, the point is that ratios compare things with 2 units and or with the same units. So ratios, and I already wrote that down. They compare things with the same units, right? And so like another example would be like if you look at payouts on, if you're going like to a casino or something and you want to gamble, right? So maybe the payouts on a certain bet are, say, like if they say 5 to 1, okay? Payouts are 5 to 1. What does it mean? Yeah, if you put $1 down and you win, you're going to win $5, okay? So we could write that ratio as a fraction. In other words, and notice that the fraction reduces, right? In other words, it's telling you it's a 5-time payout. Yeah? But you don't need units on that because do you have to bet exactly $1? You don't have to bet $1. You could bet $2 or, I mean, it depends on the casino, but you could, it's saying like you could bet $3.50 or something, or you could bet $10. the ratio just is going to be preserved. If I bet $10, I'll win 50. If I bet $5, I'll win 25, right? Okay. And so this would be this form right here. This is kind of like the ratio format. But we can also write ratios as fractions, which is going to be useful when we go to apply them in some certain circumstances. Okay. But to convert a ratio into a fraction, all you do is you just put the first number over the second number. So 5 to 1 means 5 times payout. Okay. So if I had a ratio where it was something like 15 to 40, okay, this could be like the mixture of like a medicine to like a saline solution. You need 15 milliliters of that to 40 milliliters of that. Okay. Doesn't mean you have to make exactly that much. It means you have to preserve that ratio no matter how much you use. So as a fraction, what would that be? 15 over 40. And fractions you should typically reduce, right? So this would be, this one reduces by what? 5s? So 15 divided by 5 is 3. 40 divided by 5 is 8. So 15 to 40 is the same as 3 to 8. So it's 3 parts one thing to 8 parts the other. All right. If you see ratios, you could see ratios that have decimals in them, but if you're going to convert them to fractions, so let's say, I don't know, let's say it's like, let's say 0.8 to 0.36 or something like that. Okay. Well, as a fraction, what would that be if I just take my decimals and put them in fractions? Yeah, it'd be 0.8 over 0.36. Now, I don't know, did we talk about this all, decimals inside of fractions? Okay, that's a weird way to write a fraction. You typically don't see a fraction with a decimal inside of it. Okay, well, is there a way that we could get rid of the decimals? The answer is yes. Does anybody know how, though? So think about with like when we do common denominators, you can multiply the bottom by whatever you want as long as you multiply by the top by the same number. So what we could do is, we could actually move this decimal over 2 place values by multiplying by 100. But if we do that on the bottom, we also have to do it on the top. So if you end up with a fraction that has decimals in it, you can move the decimal as many place values in either direction as long as you do it on the top and the bottom. It'll preserve it. So like this, so on the bottom we'd have 36, but since we had to move it 2 place values on the bottom, then on the top we also have to move it 2 place values. But what am I going to have to do right here? I'm going to have to fill in a 0 there to fix it. Okay. So if you end up with decimals and a fraction, that's okay. Just move them out of there. Of course, this is reducible now, I think, because 80 and 36 are both divisible by what? They're at least divisible by 2. 80 divided by 2 is 40. 36 divided by 2 I think is 18. So we probably go further than that. Those are both divisible by what? At least 2 again, right? So 40 divided by 2 is 20. 18 divided by 2 is 9. I think we're done there, right? So what it's telling you is it's saying that this ratio, 0.8 to 0.36, it's actually the same as 20 to 9. So they're the same ratio, they're just at different quantities. All right. Questions about that? Okay. All right. What if you had something like if you had fractions in there, like 1.5 to 2/3, something. And I wanted to convert it into a fraction. Yeah, so you could, the thing is that sometimes you can get away with converting to decimals, but it's not going to work here. Why won't this work by converting it to decimals? Anybody know? This one's not a problem. This you could convert to 1.5. Yeah, the problem is, I don't know. Oh, yeah, I did start my recording. I was just making sure. Yeah, the problem is that the 2/3 doesn't turn into a nice decimal, right? If you try to turn 2/3 into a decimal, it's 0.66666, right? And you can't round that because as soon as you round it as approximation, it doesn't preserve the right values. So we need to leave it as fractions, but what we should do is we should turn that into an improper, right? So 1.5. So 2 times 1 is 2 plus 1 is, that's like 3/2 to 2/3. Okay, now what should we do if we want to turn it into one single fraction? Well, what did I do before? I don't think we need a common denominator here. Like, just think back to if I was doing 2 to 5, what would that fraction be? 2/5, right? So, yeah. So sometimes when I'm dealing with fractions, it's like it seems more confusing because fractions are involved. But if you think about it, okay, well, what would I do if it was whole numbers? Okay, well, if I do as whole numbers, I just take the first thing and put it over the second thing. So we just do the same thing here. This is 3/2 to 2/3. Well, what kind of fraction? What did we just create? We created a complex fraction which we treat as a division problem. And so this is actually 3/2 divided by 2/3. But when you go to divide fractions, what should you do? You should change it to multiplication by flipping which one? The second one, the one that comes after the division sign. So this would be 3/2 times 3/2. We flip the second one, and then what is this going to become? 9/4. Okay? So, in other words, what it's telling you is it's telling you that, like, if you have a recipe and it calls for 1.5 cups flour and 2/3 brown sugar, that's the same as saying, like, 9-4. It'd be like 9, if you were going to make it that big, it'd be 9 cups of flour to 4 cups of brown sugar or something. Like if you were going to bump it up to, okay. So, all right. So anyway, so the ratios, so the idea is that if you have a ratio, typically speaking, if we're going to work with it, like if we're going to try to like expand or contract this recipe, we want to have it in fraction form because that's going to allow us to set up like some proportional equations later on that'll allow us to kind of find the amounts at any level. Okay. That's the goal. All right. So that seem okay so far? So ratio is just a comparison of two different things with the same units, and we can write them as fractions. Now, what happens, though, is that in a lot of cases, you're not necessarily comparing things that have the same units. So rates compare two values with different units. Right? And so, for example, like, let's say that a machine makes, say, 155 parts in 35 minutes. Okay. Well, it's like a ratio, right? It's like 155 parts to 35 minutes. But if I turn it into a fraction, what happens to my units? Like if I were to convert this into a fraction, 155 over 35, right? Well, 155 is parts, 35 is minutes. And it's not like the cups over cups examples where like the units cancel out. This is parts over minute. So what happens is that a unit gets preserved. Like I can't cancel out those units. So my answer, my fraction is 155 over 35, but my unit stays. Right? It's parts per minute if I compare those two values. This one happens to be reducible because they're both divisible by 5. So this would be like 30. If you divide 155 by 5, it's 31. 35, parts per minute. In other words, 155 parts in 35 minutes, it's the same as saying 31 parts every 7 minutes. Right? It's the same ratio, or it's the same rate, but my final answer has to have units. Okay? Because I'm comparing two different things with different units. You've seen this before. Like, what are some rates that you've seen before, comparing two different units? This is parts per minute, but we've also seen what?
Miles per hour.
Miles per hour is a rate. It shows you how many miles you're covering in an hour. Two different units. What else? Another similar one is what? Miles per hour. You also could talk about in the car. You could talk about sure, revolutions per minute. Okay, that's like how fast your engine's turning over. Yeah, that's two different units. Revolutions, minutes. What else? There's a bunch associated with cars that we deal with.
Kilometers per hour.
Oh yeah, you could go kilometers per hour if you switch units, go into metric. That's true. Yeah, I was thinking something else though. Miles per gallon is a rate, right? How many miles can you go on a gallon of gas? It's comparing miles, gallons. Then if you go to get gas, what do you see on the pump?
Gallons per dollar.
Flip it.
Dollars per
Yeah, you could go the other way, but that would be a confusing way to read it. Dollars per gallon, right? That's a rate. It's telling you how many dollars does it take to use a gallon. Okay, so rates compare things with two different units. That's the point. Yeah? Now, this would be, this right here, like 31 over 7 parts per minute or 150 parts in 35 minutes, you could write it that way, but it's like this is, normally speaking, when we deal with rates, we don't actually look at it on, like, another way we could think about this is, okay, so that's interesting in 35 minutes, but, for example, how many parts can it produce in 1 minute? Right, like we could reduce it down to, so if it does, I know that if it does 155 parts in 35 minutes, right, so we figured out that would reduce, so that's 155 over 35, but that reduced to 31 and 7, right, parts per minute. Okay, but that's 31 parts in every 7 minutes. Could we actually figure out how many it produces every single minute?
I actually did the math on that.
Mm-hmm.
It was 4.428571.
Yeah, you could actually perform the division. You could have actually done that before we reduced, because you'll get the same answer. But do the actual division, 31 divided by 7, and what'd you say it was? Let's round to like the nearest hundredth.
4
So-
4.3. 4.43.
Okay, 4.3,
Yeah.
if you round to the hundredths.
Yeah.
Okay, so I'm actually pulling out my calculator and doing that, 31 divided by 7. Or you could do it actually back at that step. You could just take 155 and divide by 35. Either way, they'll give you that decimal. And then the units here are the same, right? Now that's telling you parts per single minute, right? If you actually perform the calculation. And so this right here, this is what we would call the unit rate. Okay. The unit rate tells you how many of these things can I do in one of those, right? For every 1 minute. How many parts is it spitting out? It's spitting out a little over 4 parts per minute. Yeah? Unit rates are actually what we're most familiar with. So for example, if let's say that you pay $35 for 11.2 gallons of gas. Right? Okay. You could write that as a non-unit rate. So you could write that if we're just going for the rate, the non-unit rate, then we could write that as 35 over 11.2, and that would be dollars per gallon. Yeah? It's not wrong. It's just that's a really weird way to describe the price of gas to someone, right? Like if you went to the gas station and all of the prices were listed like price per 11.2 gallons, that would be a very strange thing. So what do you see instead? Instead, you see the unit rate, okay? And you say, okay, so what we'll actually do is we'll just do the division, which is, what does that come out to be? Then we'll round it to the nearest cent because we're talking about dollars. So 35 divided by 11.2, what do you get? 3.125. So that would round to like 313, right? And that would be, oops, I don't want to trash the whole thing. I'll keep the units out here. Dollars per gallon. Right? And that's the unit rate. So this rate over here, that rate's not like mathematically incorrect. It's just not a very good way to explain the rate to people. The unit rate is a much more natural way to explain things, and that's actually the way we do it. So miles per hour is a unit rate. So if you're going 60 miles per hour, what does it tell you? It tells you cover 60 miles in 1 hour. Yeah? Okay. So mostly we deal with unit rates. All right. Now, does the order you divide matter? Absolutely it matters. What if you divided the other way? What would happen? 0 point, what is it? 3.2. But what's the units here? That's the thing. See, 11.2 was the gallons, and 35 was the dollars. And so if you divide the other way, it's not wrong, it's just different. Because 313, that's the dollars per gallon. Then if you divide the other way, you get 0.32, but gallons are on top, dollars are on bottom. It's gallons per dollar. What is that telling you? Yeah, that's like if you went into the gas station and you said, I'll take $1 on pump 3, right? Then you're going to get 0.32 gallons. That's what you're going to get for $1. Whereas the flip side, it's telling you how much you're going to pay for a single gallon. So neither of them are wrong, and they're both unit rates, but you have to be careful about which one you calculate. All right? And so usually some are more intuitive. Like our speedometers don't read hours per mile. That would be a weird way for a speedometer to read. It would work. You could do it. It's just we don't. Okay. Now the reason it matters is because one of the ways that we use unit rates is you could compare items. So let's say, for example, like this happens if you go into like the grocery store and they sell things in different quantities, right? So like let's say, for example, you go into the store and they sell 2 different quantities. So let's talk about, I don't think it really matters, but let's just say we're talking about, I don't know, what's the most recent thing I bought that was in different quantities? I don't even remember, but.
Bulk items?
Sure. Yeah, well, it could be bulk, but like I'm thinking about things that are prepackaged, right? So let's say it's crackers or something, right? In the store, you can buy 2 different boxes, or the same. It's like cereal, right? Cereal's like this a lot too, right? There's like 3 different sizes of cereal, and there are all arbitrary numbers, and it doesn't. Why they do it, like nobody knows. Like why do you sell like Captain Crunch in 3 different sizes? I don't know. But whatever, they do, right? So let's say there's 2 different boxes of the same cereal, and let's say that one box is say like 18.6 ounces, and it costs let's say $3.25. Okay, and then let's say that you could buy the other box, and let's say the other box is 24 ounces. and it costs. I'm trying to think how much I want it to cost. I'm making this up, by the way, so hopefully this doesn't go all cattywampus. But let's say $4 and let's say $4.15 or something. I don't know if this is going to work out nicely or not, but whatever. Okay. Now, one of them's bigger, but it's more expensive. One of them's smaller, but it's cheaper. And the question is, okay, well, which one is the better value? That's the question.
Oh, is it the store when you see like price per ounce?
Yeah, and if the store is nice enough, they'll provide that information for you, except for lots of times the stores don't do it in the same units on the thing. Like, I've noticed on some it'll be like, this one's like 10 cents per ounce, and this one's like $3 per one. Or something, or they do like dumb unit rates, and so yes, but yeah, a lot of times they'll list them. Okay, but we could do it ourselves. It's not too bad, right? Because what we can do is we could calculate unit rates, and we could actually figure it out, right? So you could say, so for the smaller box, we could figure out, how much are you getting? Now, do you think it's more typical to do dollars per ounces or ounces per dollar? Yeah, most of us think in dollars per ounces because we're thinking money-wise, and we want to see a low dollar amount. You could do it the other way, but dollars per ounces. So let's go dollars per ounces, which means we need to do the dollar amount is $3.25, and we want to divide by 18.6. And so it's dollars over ounces. So in our calculators, that's going to be what? $3.25 divided by 18.6. All right, so what does that come out to be? Let's round it to like, I don't know, like three decimal places. I don't know if it's going to come down to being that close, but let's say 325 divided by 18.6. 0.175. Other people get that? Okay. So that one is about what? About 17.5 cents per ounce. Okay. So then you go back and you do the same thing for the large box. And you say, okay, the large box, I'm doing dollars over ounces, so the dollars go on top, the ounces go on bottom, and so that's 415 divided by 24. So you do that in your calculator, and what do you get?
0.173.
173. Oh, I did a pretty close one then. Ounce. So actually, those are pretty close. But which one is the better value? Yeah, this one right here, this one is not much, but this one is the slightly better value, right? Because it's cheaper per ounce. And so unit rates help us compare things that are in different, sizes. This is why we work with unit rates. Like if you're looking at different cars to purchase, you can compare miles per gallon, and you want high miles per gallon, So those are unit rates. All right. Seem reasonable? But again, you have to be careful because what if you accidentally divided the other way? What if you accidentally did 8.6 divided by 325 and 24 divided by 415? You get different numbers, right? So if you do 18.6 divided by 325, what do you get? 5.7. Give me like 3 decimal places. 5.7. 5.723. 5.723. And if you do 24 divided by 415, what do you get? It's going to be pretty similar. 5.783. Okay. But what happened here is that you put ounces over dollars. And so our unit would flip. Okay? Well, now you got to think, well, which one's the better value? I mean, we already know which one the better value is. Which one's the better value? It should be this one. And it actually still is, but that's the bigger unit now.
It's because you're getting more ounces per dollar.
Exactly. That's the thing. Because this one is still the better value because you're getting more ounces per dollar you pay. But So that's why you have to be really careful on problems like this, because if you divide it one way, you'd be looking for a smaller number, like our first example. I want to pay less per ounce. But if you divide it the other way, you'd actually be looking for a bigger number. I want more ounces per dollar. So the units really matter a lot. Okay, so you got to be really careful to divide the right way. Yeah? Okay. All right. Perfect. Then the only other thing that I want to mention here in chapter 5 is another place that decimals pop up a lot is when we start dealing with something called square roots, and you probably have some familiarity with that. So this will be just a really quick foray into square roots. Okay. So what the square root does is it undoes the square of a number. Okay. So, like for example, we know that 3 squared is 9. Okay. So the square root function, it looks kind of like a long division symbol, except for it's got a little tail on it or something. It looks like this. Okay. And so then 3 squared is 9. So what is the square root of 9? It's 3. It's like undoing the square function. It's like going back to the number that would be squared to get there. Okay. Now your calculator probably has a square root function in it, is my guess. You just hit 9 and then square root, and it'll spit out 3. Okay. So the same thing, like, okay, well, what's 5 squared? 25. So then that means that 25 has a square root. What's the square root of 25? It's 5. Okay. Now things like 9 and 25, or like 9 and 25, these are numbers that we call perfect squares. And the terminology is not that important, but the reason we call them perfect squares is because they have a number that you could square to get up to them. So the perfect squares are numbers like 1, 4, 9. Why am I having a problem thinking today? 16, 25. All those numbers that constitute perfect squares. But what happens is sometimes you'll have numbers that don't have perfect square roots. So, like the square root, the square root of 36 exists, right? What is the square root of 36? It's got to be 6, because 6 squared is 36, and your calculator will confirm it. But what happens if I try to take the square root of 30? Yeah, it won't work because, see, 5 squared is 25, 6 squared is 36, but then, what number squared gives you 30? There is no actual number, right? There's no whole number that'll get you 30 if you square it. So, but what you can do is you can approximate it. Remember I told you this symbol right here? It means approximately. So if you plug it in your calculator, what does it tell you? It tells you it's 5 point what? 47225 ... Square roots of numbers that don't have square roots, perfect square roots, they're like pi. They have decimals that go forever and never repeat. But we can round them, right? So we could say that that's about, 5.47. Okay, so that's possible, all right? So when you're dealing with square root functions, which we will occasionally later on, if it has a perfect square, great, you get a nice whole number. If it doesn't have a perfect square, that's okay because you can approximate it as much as you need to. Okay, so then you get decimals out of that. There's one thing you have to be really careful about. So the square root of 36 we decided is 6. What's the square root of negative 36?
6.
Well, you think. So 6 times 6 is 36. So it can't be 6 because 6 times 6 is positive 6.
So it'd be -6.
What about negative 6 times negative 6? Yeah, that you got a problem. See, that's the thing, because when you square a number, you turn it positive. Like if you take a negative number and square it, you get this negative times negative. It always goes back to positive. There's no way to take any number and square it and get a negative number. And so the answer here is it doesn't exist, okay? So there's no answer. You just say, we call it not a real number. And actually, you can try it in your calculator. If you can plug negative numbers on your calculator, type in 36 and then negate it, and then try to take the square root of it. What does it say? Error. Like your calculator just yells at you because it's not possible. So the one thing about square roots is, so if it's if it's the square root of a nice number like 36, that's easy. If it's the square root of a not so nice number, that's okay. We can approximate it. But if you get into the square root of negative numbers, you can't take the square root of a negative number, okay? So you can't take the square root of a negative number. It's like a big no-no. Okay. It's like dividing by 0. Okay. You can't divide by 0, and you can't take the square root of negative numbers. It's not so. If you ever see that, then this is not a real number. That's what you would say. Some calculators will go NaN. That's what they'll spit out, and that's what they're telling you. They're saying not a real number. Some calculators will call it. Sometimes you'll see it called undefined. Sometimes like division by 0, but we'll use the not a real number. So that's the key. Can you have a negative outside the square root? That's not a problem, because order of operations, the square root is kind of on the level of parentheses or exponents. And so you could take, if the negative is outside the square root, there's no problem. You can just take the square root of 36, which is 6, and then apply the negative at the end. So if the negative is outside, no big deal. If the negative is under the root, that's a big deal. It's a problem. Don't do it. It's not a real number. Okay? All right. So I got a couple practice problems here for you guys to take a look at. I don't think you'll have time to finish these and go over the solutions today, so we'll just go over them on Monday, but I'll just hand them out in case you want to look at them today or take them home. And then make sure if you haven't taken that first chapter 5 quiz, that you take that today. I think your second chapter 5 quiz is due next week. I'll take those today too, actually, yeah. But you should, there's a stack up there if you want to throw. Yeah. And if you do have your test corrections, make sure I get those today.